Welcome back to the deep dive. We are doing something a little different today. Usually when we talk about space, we talk about things we can see, stars, galaxies, nebulas. But today we're tackling the invisible.
We're going after the monsters in the dark.
We are talking about black holes. But, and here's the kicker, I think most of us, myself included, have the wrong picture in our hands.
Oh, that's entirely possible. I'd say black holes are probably the most misunderstood objects in the entire scientific canon.
Exactly. Because if I asked you, or if I asked the listener right now, what is a black hole? The answer is almost always the same. It's a cosmic vacuum cleaner.
A trapdoor, yeah.
The ultimate prison where you check in, but you never check out. Nothing escapes, not even light. That's the headline we've been fed by sci-fi and, high school physics for decades.
And that's a classical definition. For a long time, that was the scientific definition, too. An event horizon was seen as a one-way membrane. Simple as that.
Right. But the source material we're diving into today, which focuses on that sweet spot where general relativity crashes into quantum mechanics, basically tells us that common knowledge is dead wrong. The hook that grabbed me, and the reason we're doing this, is a paradox that Hawking presents. Black holes ain't so black.
It's a provocative statement, to say the least.
It is. The text claims they glow, they shrink, and eventually they explode with the force of 1,000,000 nuclear bombs.
Which sounds like the exact opposite of a black hole.
It sounds like a complete contradiction.
It does, but it's actually the inevitable result if you take all the laws of physics seriously, not just some of them. Our mission today is to walk through exactly how we get from eternal dark prison to glowing, exploding engine.
And to do that, we have to travel back in time a bit. The source material sets the scene really beautifully. We're in November 1970. We're looking at Stephen Hawking.
A very specific, very human moment in his life.
Yeah, shortly after the birth of his daughter Lucy.
It's a pivotal time for him, both personally and professionally. And the text highlights something quite intimate about his process. By 1970, his disability ALS was already significantly affecting his motor functions.
Right. The simple act of getting into bed wasn't simple at all.
No, not at all. It was a slow, arduous process. But Hawking notes, and I think this is such a testament to his resilience, that because it took so long, it gave him time.
Time to think.
Exactly. While his body was struggling with the physical mechanics of moving, his mind was just free to roam through the geometry of space-time. He was visualizing the universe while he was putting on his pajamas.
I love that image. The rest of the house is quiet, the world is asleep, and he's there, mentally grappling with the architecture of the cosmos.
And he starts chewing on this core question: how do we actually define the boundary of a black hole?
The event horizon.
This is the foundation. If we want to understand how a black hole dies, we first have to understand what defines its life. In 1970, the definition was a bit fuzzy. Physicists knew it was the point of no return, but
they didn't have a precise, agreed-upon geometric definition.
Right. Hawking and Roger Penrose were trying to pin this down. They eventually settled on the idea that the black hole is the set of events from which it is not possible to escape to a large distance.
Okay, set of events is a little abstract for me. The source uses a visualization that I found much more helpful. It talks about light rays.
It's much easier to visualize with light. Imagine a star collapsing. It gets denser and denser.
Gravity gets stronger and stronger.
Right. Now imagine a flash of light goes off at the center. The light rays try to race outward, but gravity is pulling them back, like dragging a heavy stone up a really steep hill.
Some fall back in. Some escape.
Correct. But there is a critical boundary. There are light rays that just fail to escape. They don't have enough energy to break free, but they have just enough not to fall back in immediately.
So they're just hovering there, frozen on the edge.
Effectively, yes. The event horizon is formed by these light rays. They are the sentinels of the boundary.
The text uses an analogy here that I think everyone can relate to. It compares these light rays to running away from the police.
It's a vivid image for sure.
It says, imagine you're running away from the police. You're sprinting. You're going as fast as you possibly can. But the police are just as fast as you are.
You are pushing your body to the absolute limit.
Exactly. You're managing to keep one step ahead. They aren't catching you, but you aren't pulling away either. You're running at full speed, but relative to the danger, you're stuck in place.
That is the event horizon. Those light rays are sprinting outward at the speed of light, 300,000 kilometers per second, but the space beneath them is collapsing inward at the same speed, so they hover.
So that night in 1970, as Hawking is getting into bed, he has this epiphany about these running light rays. he realizes something about their geometry.
Something crucial.
He realizes that the paths of these light rays can never approach one another.
This is a subtle but massive realization.
Why? Why can't they get closer?
Well, go back to the police analogy. Imagine you're running away, and there's another fugitive running right next to you. You're both right on the edge of getting caught. If your paths converge, if you run into each other, what happens?
We crash, we trip.
You crash, you lose momentum, and if you lose momentum...
The police catch us, we're done for.
Exactly. In the black hole context, if the light rays on the horizon collide, they fall into the hole. But if they fall in, they're no longer on the boundary, they're inside.
Right. That makes sense.
So, by definition, any light ray that remains on the boundary must be moving parallel to its neighbors or moving away from them. They can never, ever run into each other.
Okay, I follow the geometry. It's like a shadow, right? The source mentions a shadow analogy.
Yeah, the shadow of impending doom. If you look at the shadow cast by a distant object, like the sun, the rays defining the edge of the shadow don't cross. If they crossed, the shadow would get smaller and vanish.
So we have this rule. The rays on the boundary cannot converge. Why was Hawking so excited about this? The text says he was so excited he couldn't sleep.
Because of the implication. If the rays on the boundary can never get closer together, it means the total area of the boundary, the surface area of the black hole, can never decrease.
The area law.
The area law. Think about it. If the rays got closer, the bundle of rays would shrink and the area would go down. But since they can't approach, the area can only stay the same or get bigger.
So the black hole can only grow. It can never shrink.
That was the conclusion, yeah.
Let's stress test that. If I throw a refrigerator into a black hole.
You add mass to the hole, gravity gets stronger, the horizon expands, the area increases. Law satisfied.
Okay. What if I take two black holes and smash them together? That's a violent event. Surely things get messy there.
It is unbelievably violent, but the law holds. If two black holes collide and merge to form a single new black hole, the surface area of that new black hole must be greater than or equal to the sum of the surface areas of the original two.
So it's a one-way street. The universe allows black holes to get fatter, but forbids them from going on a diet.
That was the consensus in the early 70s. It was called the non-decreasing property. It felt like a fundamental truth of the cosmos. Hawking called Roger Penrose the next day, and Penrose agreed. It seemed ironclad. But
There's always a but.
there is. This property that the area always increases started to nag at people. It reminded physicists of something else. It looks suspiciously like another famous law of physics.
Entropy.
Entropy.
Now, I feel like entropy is one of those words people throw around at parties to sound smart or to explain why their teenage son's room is messy. It's just entropy, Mom.
Chuckles. It is the ultimate excuse, isn't it?
But in physics, it's a very specific, rigorous measurement. So before we connect it to black holes, let's make sure we actually understand what entropy is.
Sure. At its core, entropy is a measure of the disorder of a system. Or, to be more precise, it's a measure of how many ways you can arrange the insides of a system so it looks the same on the outside. But disorder works well for our purposes.
Okay. Order versus disorder.
Right. And the second law of thermodynamics is the rule that governs this. It states that the entropy of an isolated system always increases.
Things naturally fall apart. The center cannot hold.
It really can't. If you build a sandcastle, the wind and waves will eventually erode it back into a smooth beach. The beach, the disordered state, is high entropy. The castle, the ordered state, is low entropy. The universe pushes everything toward the beach. It never spontaneously pushes the sand back into a castle.
The source uses a box of gas analogy to illustrate this. I think this helps visualize the mechanics of it.
It's a classic thought experiment. Imagine a box. Inside, you have billions of gas molecules bouncing around like microscopic billiard balls.
Okay.
Now imagine we insert a partition, a wall, down the middle of the box, and we manage to trap all the molecules on just the left side.
So the right side is empty, the left side is full, it's organized.
Exactly. That is a state of order. We know something about where the molecules are. We know they are all on the left. That is low entropy.
Got it.
Now we pull the partition out, what happens?
They rush to fill the space. They spread out all over the place.
Chaos. They mix. They fill the whole box. They become disordered. Now, if you pick a spot in the box, you don't really know if a molecule is there or not. The information is hidden. The entropy has increased.
And the crucial part is that they never go back.
Never. You could sit and watch that box for 1 trillion years. The odds of all those billions of molecules accidentally bouncing in just the right way to end up back on the left side at the exact same moment, It's statistically zero. It just doesn't happen.
So entropy goes up. It's a one-way arrow of time.
Just like the size of a black hole?
I see the parallel now. Area always goes up. Entropy always goes up. They look like the same graph.
They do, and this similarity didn't just go unnoticed. It caused a crisis.
A crisis. I would think physicists would be happy that the laws match up. Oh, look, nature is consistent.
You would think, but it actually created a massive logical problem, and it involves a loophole.
A loophole in the second law.
A huge one. Imagine you have that box of gas we just talked about. It's full of high entropy. It's a mess. Now, imagine you throw that box into a black hole.
Okay. I toss it in. Goodbye, messy box.
It crosses the event horizon. It is gone. It is no longer accessible to our universe.
Right.
So, for an observer standing outside the black hole, the total entropy of the universe just went down.
Oh, I see. I took the mess and I deleted it from existence.
Exactly. You scrubbed the disorder from the cosmos.
Which violates the second law of thermodynamics.
It breaks the most sacred law in physics. It suggests that black holes are cosmic trash cans where you can hide your entropy. If the second law is universal, that shouldn't be allowed.
But wait a minute. We know the box is still in there? Can't we just say the entropy is still there, it's just inside the hole?
That was the initial reaction. It's hidden. But physics is built on what you can measure. If you can't measure it, if you can't see it, if it has no effect on the outside world, it doesn't really exist in a physical sense.
It's a philosophical problem.
It's a physics problem. If the black hole simply swallows entropy and shows no sign of it, the second law is broken for all practical purposes. There needed to be a way for the observer outside to know that the black hole was carrying that burden of disorder.
So the black hole itself needs to have entropy.
Exactly. And this is where a student steps into the ring. A research student at Princeton named Jacob Bekenstein.
Enter Bekenstein.
Bekenstein looked at Hawking's area law, this idea that the area never decreases, and he had a moment of brilliance. He said, look, we have this problem with entropy disappearing. We have this black hole area that always grows. Maybe they are the same thing.
He just connected them, equated the size of the hole with its messiness.
Yes. He proposed that the area of the event horizon is the measure of the black hole's entropy.
That seems almost too simple, too elegant.
It's incredibly elegant. Think about the accounting. You throw the box of gas in, the entropy of the outside world goes down, but to UT, the black hole swallows the mass, so it gets bigger, its area increases.
So the entropy of the black hole goes up.
Exactly. And Bekenstein argued that the increase in the black hole's area is always enough to compensate for the entropy lost from the gas. The total sum entropy outside plus area of the hole never goes down.
The books are balanced. The second law is safe. Problem solved.
It was a beautiful solution, but there was a catch. A massive fatal flaw in the logic, or so everyone thought, and Hawking was the first one to point it out.
Of course he was. What was the flaw?
It comes down to thermodynamics. If a black hole has entropy, it implies, by the fundamental laws of heat, that it must also have a temperature.
Okay, that makes sense.
And if something has a temperature, think about a hot poker in a fire, or even your own body.
It radiates heat, it glows, it emits energy.
Everything with a temperature above absolute zero emits radiation. Everything. So if Bekenstein was right, and black holes have entropy, then black holes must have a temperature. And if they have a temperature, they must emit radiation.
But they are black holes. The whole point is that they're black.
Exactly.
The whole definition is that they don't emit anything. That's the first thing you learn.
That was the contradiction. Bekenstein's idea saved the second law, but it seemed to destroy the very definition of a black hole. Hawking looked at this and said, this can't be right.
He didn't just think it was wrong. The text implies he was actually kind of annoyed.
Yeah.
Like personally offended.
He really was. He felt Bekenstein had misused his area law discovery. He even wrote a paper with Brandon Carter and Jim Bardeen specifically to point out this fatal difficulty, basically saying, nice try, kid, but black holes don't have a temperature because they don't radiate. Case closed.
So Hawking is sitting there firmly in the camp of black holes are black. Dead, cold, silent.
Correct. Until he took a trip.
Moscow, 1973.
In Moscow. He goes to meet with the leading minds of Soviet physics, Yakov Zeldovich and Alexander Starobinsky.
Now, Zeldovich is a legend. He was one of the fathers of the Soviet atomic bomb, right? Not someone you just dismiss.
A brilliant, formidable intellect. And these two sat Hawking down and they told him, Stephen, you are missing something.
What was he missing?
They told him he was looking at the problem purely through the lens of general relativity gravity. But he was ignoring quantum mechanics, the physics of particles and the very small.
He was looking at the stage but ignoring the actors on it.
That's a nice analogy. They argued that if you applied the quantum mechanical uncertainty principle to a rotating black hole, the energy of the rotation should create particles near the event horizon.
So it spins, it spits.
That was their theory. The rotation flings particles out. Now, Hawking listened. He respected them. But he didn't like their math.
Why not? Too messy.
Yeah, he thought their calculation method was a bit hand-wavy. It wasn't rigorous enough for his taste. So, being Hawking, he went home to Cambridge with a mission. He was going to redo their calculation, but do it properly.
He wanted to prove it with better, more elegant math.
Yes, and he fully expected to confirm their result. That rotating holes emit radiation, but stationary ones do not. That was his goal.
He went in with a clear expectation.
He did. He spent months on this, developing a new mathematical treatment. And when he finally got the answer, he was shocked.
Why? What did the math say?
The math told him that even non-rotating black holes emit particles.
Even the dead, still ones. The simple ones.
Even the simplest, quietest black hole in the universe is glowing.
That must have been a moment of panic, like, I broke the math.
He admits in the text to surprise and annoyance. His first thought was that he made a mistake. He checked his approximations. He was actually worried that Bekenstein would find out and say, "I told you so."
Because if they emit particles, they have a temperature. And if they have a temperature, they have entropy. Bekenstein was right all along.
Bekenstein was right. Hawking tried to find the error, but the more he checked, the more the math held up. The emission spectrum of the particles matched exactly what you would expect from a hot body. The rate of emission was exactly right to prevent violations of the second law. It was undeniable.
So, despite his initial annoyance, he had to accept it. Black holes aren't black. They emit what we now call Hawking radiation.
A complete paradigm shift, born out of trying to prove the opposite.
Okay, so we've established that it happens. The math works. But the part that breaks my brain is how. How does empty space, literal nothingness, suddenly generate particles?
This brings us to the mechanism. And you have to prepare yourself because we are leaving the world of common sense and entering the quantum realm.
I'm ready. Walk me through it.
First, we have to delete the idea of empty space from your mind. Just get rid of it.
Okay. Deleted. No such thing as empty.
In classical physics, a vacuum is truly empty. Nothing there. But in quantum mechanics, empty space is actually teeming with activity. It is filled with fields, gravitational fields, electromagnetic fields.
Like invisible webs stretching across the universe.
Right. Now, the uncertainty principle, which is the absolute heart of quantum mechanics, tells us something profound about these fields. It says you can't know the value of a field and its rate of change exactly at zero at the same time.
Who'd unpack that for me? Why not?
Well, if a field were perfectly zero, meaning completely empty and still, and it stayed perfectly zero, you would know both its position zero and its velocity zero perfectly.
And the uncertainty principle forbids perfect knowledge of both at the same time.
Exactly. Nature refuses to be pinned down that precisely. So the field cannot be exactly zero. There must be a certain amount of jitter, a wobble, a baseline of uncertainty.
Quantum jitters.
I like that. We call them quantum fluctuations. And here is the wild part. You can visualize these fluctuations as particles. They appear in pairs.
Out of thin air. Just poof.
Out of the energy of the field, yeah. A particle and an antiparticle pop into existence. They move apart for a split second, then snap back together and annihilate each other.
Pop, snap, gone.
Pop, snap, gone. Net energy change, zero. They borrow energy from the vacuum and pay it back instantly.
And this is happening everywhere. Right now in this room.
Everywhere, all the time. Trillions of times a second in every cubic centimeter of space. They are called virtual particles.
Why virtual?
Because they don't last long enough to be measured directly. You can't catch one with a Geiger counter. But we know they exist because they have tiny indirect effects on things we can measure, like the shifts in electron orbits in an atom.
Okay, so space is a bubbling soup of these ghost particles appearing and disappearing. What happens when you put a black hole in the middle of that soup?
The event horizon disrupts the dance. Imagine a pair appears right on the very edge. One particle is just outside the line, and the other is just inside.
The police are chasing them. One gets away, one doesn't.
And gravity is pulling. The gravity is so intense right at the horizon that it can pull the pair apart before they have a chance to snap back together and annihilate.
The reunion is canceled.
Permanently. One particle falls into the hole. The other one, finding itself without a partner to annihilate with, is now free. It escapes out to infinity.
To an observer far away, what does that look like?
It looks like the black hole just spat out a particle. It looks like radiation coming from the direction of the hole.
Okay, I'm with you on the visualization, but I'm going to stop you here because there's a rule in physics that I thought was unbreakable. You don't get a free lunch. Energy cannot be created from nothing.
Conservation of energy. Yeah.
Right. If a real particle escapes, that's real energy entering the universe.
Mm.
Who is paying the bill for that? Where did that energy come from?
The black hole pays the bill.
Wow.
This is the trickiest concept in the entire chapter, so stick with me. We have to talk about negative energy.
Negative energy. That sounds like something a villain uses in a comic book.
Yeah.
I will blast you with my negative energy beam.
Chuckles. It does sound sci-fi. But it's a real concept in gravity. Think of it this way. Energy must be conserved. So for the escaping particle to have positive energy, which it must to be real, its partner that fell in must have negative energy.
But how can a particle have negative energy? Does it have negative mass or something?
It's not intrinsic to the particle. It's about its relationship with gravity. Think about this. Far away from the black hole, space is flat. Energy is positive. That's our baseline.
Okay, baseline is positive energy.
But as you get close to a massive body, gravity pulls on you. To get away, you have to expend energy. You have to pay to climb out of the gravity well.
Like climbing out of a pit. You lose energy as you climb.
Exactly. Now imagine you are inside the pit. Inside the black hole, the gravitational pull is so extreme that the debt you owe to gravity is enormous. It's so large that it outweighs the normal mass energy of the particle itself. So the total energy of that particle relative to the outside world becomes negative.
So the particle that falls in is essentially a bad check. It's an IOU, a debt.
That is a perfect way to put it. The black hole swallows a debt.
And if you swallow a debt, your net worth goes down.
Exactly. Einstein's famous equation, EP-mc², says energy equals mass. So if negative energy flows into the hole,
you're subtracting mass from it.
The black hole gets lighter.
That is absolutely mind-blowing. So the black hole is shrinking, not by spitting things out, but by eating these negative energy particles.
It is evaporating.
Right.
It is literally paying for the radiation it creates with its own body mass.
This changes everything. We used to think black holes were these static internal monuments, but this says they are dying. They are leaking. They have a lifespan.
It sets up a life cycle.
Yeah.
And it's a dramatic one. The text describes it as a runaway process.
Why run away? Why doesn't it just leak steadily like a dripping faucet?
Because of the temperature. Now, this is going to sound completely backwards. Usually a smaller fire is cooler, right? A match is cooler than a bonfire.
Sure. Less fuel, less heat.
For black holes, it is the exact opposite. The temperature of a black hole is inversely proportional to its mass.
Yeah.
The smaller it is, the hotter it is.
Wait. So a huge, supermassive black hole at the center of a galaxy is cold.
Almost absolute zero. Incredibly, incredibly cold.
And a tiny microscopic black hole is hot.
Blazing hot. So think about the cycle. The black hole emits radiation.
It loses mass.
So it gets smaller.
And because it gets smaller.
It gets hotter.
And if it gets hotter.
It radiates faster.
And if it radiates faster.
It loses mass even faster, which makes it smaller, which makes it hotter, which makes it radiate faster. It's a death spiral.
It accelerates. It's a feedback loop.
It accelerates drastically. A massive black hole evaporates very, very slowly for eons. But as it gets tiny, it goes critical. The last few moments are violent.
What happens at the very end? When it's the size of a microbe or an atom?
The text says the theory gets a bit hazy on the final nanosecond because we don't have a full theory of quantum gravity yet. But the most reasonable guess is that it disappears completely in a tremendous final burst of emission.
An explosion.
A massive explosion, equivalent to millions of hydrogen bombs going off all at once.
Wow. So every black hole is technically a ticking time bomb.
Technically, yes.
But the timer.
Yeah.
We need to talk about the timer. Because if the sun became a black hole, do I need to worry about it exploding next Tuesday?
You chuckles. No, you do not. The timescales here are astronomical, literally. The text gives us the numbers. A black hole with the mass of the sun has a temperature of about 1/10,000,000th of a degree above absolute zero.
That is incredibly cold. Colder
Yeah.
than anything.
It is colder than space itself. The cosmic microwave background, the leftover heat from the Big Bang, is about 2.7 Kelvin. So right now, a sun-sized black hole is actually absorbing more heat from the universe than it is emitting. It's freezing, not evaporating. It's getting fatter.
So it won't even start shrinking until the universe cools down below that tiny fraction of a degree.
Exactly. It has to wait for the universe to essentially freeze over. And the time it would take to completely evaporate is represented by the number 1 with 66 zeros after it, 1066.
That is, well, the age of the universe is only 10 years. So we're talking about time scales that are essentially eternity to us.
For stellar black holes, the ones formed by dead stars, yes, we will never see one explode. It's a theoretical inevitability, not an observational reality. But
There's another kind.
the chapter introduces another character here, a different type of black hole, one that might be exploding right now as we speak.
Primordial black holes.
Yes.
PBHs. I love this concept. So standard black holes come from collapsing stars. Stars are big, so the black holes are big, at least a few times the mass of the sun. Where do these primordial ones come from?
These would have formed in the very early universe, right after the Big Bang.
Oh, there were no stars yet.
Exactly. The idea is that the early universe wasn't perfectly smooth. It was a chaotic, hot, lumpy soup. There were irregularities. Some regions were way denser than others.
Lumps in oatmeal.
Perfect analogy.
Yeah.
And the pressures were so high that these dense lumps could be crushed into black holes directly. No star needed. Just brute force pressure from the Big Bang itself.
And because they weren't formed by stars, they don't have to be star-sized. They could be any size.
Correct. They could be huge or they could be tiny.
How tiny are we talking?
The text mentions a PBH with an initial mass of 1,000 million tons.
1 billion tons. That sounds heavy. That's like a mountain, isn't it?
It's about the mass of Mount Everest. But think about density. If you crush Mount Everest into a black hole, how big do you think it is?
Well,
small. The size of a car. A marble.
it would be smaller than a millionth of an inch, roughly the size of an atomic nucleus, a proton.
A mountain crushed to the size of a proton. That is just terrifying density.
It is. And remember our rule. Small means hot.
So these things aren't cold like the sun-sized ones.
Far from it. A PBH of that size, a proton-sized mountain, would be reaching the end of its life right about now. It would be blazing. It would be emitting X-rays and gamma rays furiously. It would be radiating energy at a rate of about 10,000 megawatts.
10,000 megawatts. That's, what, 10 large nuclear power plants?
Roughly, yes, from an object the size of a proton. And the text makes a funny point here. These objects are technically black holes, but they hardly deserve the name black. They are white hot.
Okay, naturally my brain goes to, can we use it? If there's a battery the size of an atom putting out 10,000 megawatts floating around space, can we hook a wire to it?
Hawking actually addresses this. He asks if we could harness the power. It's the ultimate energy source. But there is a practical problem. Aside from the deadly gamma radiation that would fry us.
Chuckles. Aside from that minor detail, it's the handling. It's the size of a nucleus but weighs as much as a mountain.
Yeah.
If you found one and somehow brought it to Earth, you couldn't put it on a table.
It would just fall through the table?
It would pass through the table like a ghost. It would pass through the concrete floor. It would pass through the Earth's crust.
It would act like a hot knife through butter.
Gravity would pull it straight down to the center of the Earth.
And then what? Does it eat the Earth from the inside out?
Not immediately. It's tiny. It would fall to the center, overshoot because of momentum, go all the way to the other side of the Earth, stop, fall back. It would oscillate back and forth through the planet forever.
Just drilling a microscopic tunnel of destruction back and forth through the core.
Probably not ideal for a power plant, no.
Okay, so we can't bring it here.
Yeah.
That's a shame.
The only solution Hawking suggests, and he admits this isn't exactly practical for next year, is to keep it in orbit. You would have to tow it.
Tow a black hole. How do you hook a chain to something that eats chains?
You don't touch it. You use gravity. You put a large mass in front of it, like a carrot in front of a donkey, and use the gravitational attraction to tow it into orbit around the Earth. Then you could beam the energy down.
I love that visual. A space tugboat dangling a heavy rock in front of a microscopic black hole to lead it home. Okay, so harnessing them is science fiction for now. But what about just finding them? If they're exploding, shouldn't we see them?
That is the hunt. Since 1974, people have been looking. We look for the gamma rays.
But space is full of gamma rays, isn't it? It's a noisy background.
That's the issue. Observations show a general background of gamma rays, but we can't be sure if they are from PBHs or other processes. However, the data sets a limit. It tells us there can't be more than an average of 300 PDHs per cubic light year.
300 per cubic light year. That sounds like a lot.
It sounds like a lot, but space is big. It means they make up at most 1/1,000,000th of the matter in the universe, so they are rare.
What if we look closer to home? The source says gravity would concentrate them near galaxies.
Right. If they're clustered in our galaxy's halo, the nearest one might be as far away as Pluto.
Pluto is far, but it's in our neighborhood. Could we spot a 10,000 megawatt light bulb at Pluto's distance?
It's surprisingly hard because they emit gamma rays, which act like particles or quanta. You need to detect enough of them arriving in a short time to distinguish the signal from the random background noise. The text suggests we would need a detector larger than anything we've ever built, placed in space, because our atmosphere blocks gamma rays.
So spotting a stable one is hard. What about the explosions? You said they end with a force of millions of H-bombs. That should be visible.
That is the best bet. We need to look for short, intense bursts of gamma rays. And actually, there's a fascinating historical connection here mentioned in the text.
Oh, this is the part about the satellites, right? The Cold War satellites.
Yes. In the 60s and 70s, the U.S. launched Vela satellites. They were built to monitor the Nuclear Test Ban Treaty. They were looking for nuclear flashes on Earth.
They were spying on the Soviets to see if they were testing bombs in the atmosphere.
Exactly. But they started detecting bursts of gamma rays coming from space, not from Earth.
They were looking down, but they found signals coming from above.
These bursts happen about 16 times a month and seem uniformly distributed across the sky, meaning they're coming from deep space. This was a big discovery. They are called gamma ray bursts, or GRBs.
So, are these the black holes exploding? Is this a smoking gun?
Hawking says he would like them to be. He's rooting for his theory, but he admits that other things, like colliding neutron stars, could explain them. And as we've learned more since the 70s, it seems most GRBs are indeed colliding stars or collapsing massive stars, but the search for the specific signature of a PBH explosion continues.
It's interesting, though. Even if we don't find them, their absence tells us something profound about the Big Bang, doesn't it?
It acts as a probe. Remember, PBHs form from irregularities, from chaos in the early universe. If we don't find many PBHs, it means the early universe was very, very smooth and uniform. So by looking for these tiny black holes, we are actually measuring the texture of the Big Bang itself.
That brings us to the broader implications. This isn't just about weird little black holes. This discovery changed how we do physics.
Oh, completely. It was the first unified theory moment. Physics is usually divided into two camps: general relativity for the big stuff, stars, gravity, and quantum mechanics for the small stuff, atoms, particles. And they usually hate each other. They don't mix mathematically.
But here they had to. There was no other way.
Hawking radiation depends essentially on both. You need the curved spacetime of relativity to create the event horizon, and you need the uncertainty principle from quantum mechanics to create the particles. It forced these two theories to shake hands.
And initially people didn't like it.
No, not at all. The text mentions a physicist, John G. Taylor, who called it nonsense and wrote a paper attacking it. It was too radical. But the logic was just too strong. Eventually, it became accepted as one of the most beautiful results in theoretical physics.
There's also a philosophical angle here regarding the fate of the astronaut. I found this kind of dark, but also funny.
It is a bit dark. If an astronaut falls into a black hole, their mass is added to the hole.
So the hole gets bigger, it weighs more.
But then over billions and billions of years, the hole evaporates. That mass is converted into energy and radiated away as Hawking radiation.
So in a way, the astronaut comes back out.
Hawking calls it a recycling, but he warns it is a poor sort of immortality.
Because the particles coming out aren't the astronaut anymore. They're not even the same particles.
Not at all. The particles are random thermal radiation. The structure is gone. The memories, the biology, the astronaut's favorite song, it's all scrambled into heat. Only the raw mass and energy survives.
So you're returned to the universe, but as a featureless scramble of gamma rays. Not exactly a comforting thought for the afterlife.
But scientifically, it suggests that gravitational collapse isn't final. It isn't irreversible. The black hole eventually disappears. And this has a massive implication for singularities.
Those points of infinite density where physics just breaks down.
Right. General relativity predicts that at the center of a black hole there is a singularity, a point where density is infinite and the laws of physics stop working. It's a breakdown of the theory. But the fact that the black hole evaporates suggests that quantum mechanics might smear out that singularity.
It softens the sharp edges of infinity.
Exactly. It hints that maybe, just maybe, the universe doesn't have these hard edges where prediction becomes impossible. It led Hawking to develop whole new approaches to understand the origin of the universe without these breakdown points.
So let's bring this all home. What's the big takeaway here for the listener? We started this deep dive with one picture of a black hole and ended with something completely different.
I think the big shift is in how we view the void. We started with the idea of a black hole as a dead end, an eternal dark room. We ended with a black hole that is a dynamic engine. It interacts with the quantum vacuum, it glows, it shrinks, it explodes, it recycles energy back into the universe.
And fundamentally changes our picture of empty space. Space isn't an empty stage where things happen. It is an active participant in the drama.
Precisely. And it connects the very large gravity with the very small quantum particles. It shows that you cannot understand the cosmos by looking at just one or the other. You need both to get the full picture.
And it leaves us with a really provocative thought to end on. We talked about the astronaut getting scrambled.
Right. The information about him is lost.
If black holes eventually evaporate and disappear completely, and if they destroy the structure of everything that fell in, the astronaut, the encyclopedia, the star, then what happens to the information that made those things what they were?
This is the information paradox, and it's a huge fight in physics. If I burn a book, in theory, I could reconstruct the text. If I gathered every photon and every ash particle, the information is scrambled but not lost. But if a black hole evaporates into purely random heat, does that information disappear from the universe entirely?
Does the history of the universe get erased, bit by bit?
If the past dissolves into random radiation, can we truly trace the history of the universe backward? Or are there parts of our history that are just deleted forever? It's a question that physicists are still fighting over today. Hawking, for a long time, bet that information is lost.
A question for another deep dive, perhaps. For now, we will leave you with that image. The dark stars are actually white hot, and nothing lasts forever, not even a black hole.
Right.
Thanks for listening.
Thank you.